Okay, I believe it is recording. So, welcome everyone. We're in our first meeting for Cohort 8 in Chapter 2. So, we'll head over to the Chapter 2 page and to Chapter 2 in the book. And let's just begin. Does anyone have any thoughts, quotes, sections that they'd like to pick up with about Chapter 2? Like, what was something that stayed with them about Chapter 2? Whether just a phrase or what is the low road? What did you expect the low road to be? What did you walk away feeling that the low road was?
Yeah, like the question I just had. So just tell me when that's most relevant place to put that question into the
Yeah,
audience.
maybe ask again just to be clear.
So I feel there are two levels of looking at the text when we talk about the action perception cycle. And it says that we have preferences, but it can be interpreted, I think, in two ways: the body having preferences, or me as the experiencing subject having those preferences. And so it feels like it alternates between those cycles as if it's the same thing. At least it does not distinguish quite clearly between those two levels of looking at it. And I was thinking, is this distinction even analytically justified? And second, if so, how then should one alternate between those two lenses?
Obviously, there's a lot of ways to go into that. Just to respond narrowly and analytically, active inference does not require a nested or a multi-level model. The first part of the book is going to build up towards just looking at single layer models. So not going into higher order human type cognition, differentiating between minds and bodies and aware and subconscious and multiple types of experiences and all of this. It doesn't have to be an embodied system. We could just be talking about a dynamical oscillating system, or even simpler systems where bringing out this framework would be total overkill. So, no specific type of articulation between any kind of body and mind is presupposed by the framework at all, which is why it almost always comes back to active inference saying less so you can say more. So the inquiry starts to look like you posit a kind of structure for a given body and mind and experiencer. And then what kinds of experiments or measurements reduce your uncertainty about that space of hypotheses? But it's not to be found in the framework.
I do acknowledge the general class of subject matter of active inference, but I do also claim that we as humans fall under the subject matter. We are a cell systems, and therefore we are also subjected to this notion of having these preferences, like also statical dynamical systems could have those preferences. But then, preferences seem to have a double layer. We experience ourselves as having preferences, and most of the times we are like conscious of it. And those preferences ascribed to us by the active inference paradigm. And then how do these two notions relate to each other?
So it sounds like you're trying to distinguish between two sets of preferences. Is that right?
The preferences we should have by the active inference framework, which sees us as systems, and we have preferences like those are like the tendencies we see as systems to evolve towards and to also to avoid entropy. Those kind of preferences ascribed by the active inference framework, but also the active preferences we as normal humans seem to experience, that we have a certain will and a certain desire and a wish to go to certain states and those things seem to contradict at first glance for me, with depression or like the suicidal tendencies,
Yeah.
etc., etc. So how do you feel about this?
So the appeal to me so far has been that I think those personal preferences are also dictated by these sort of like entropic forces that steer us towards, I don't know, towards like a set of preferences that is I don't know how
Well,
to explain it yet, but
just to throw it in, because I also thought about certain kind of relationships as such, but someone can, for example, smoke, having full consciousness about the harmful effects, about its
yeah.
reducing his lifespan, destroying his lungs,
Mhm.
and yet do the act of smoking. So how does those two things relate then, you think?
So I think this is like the one of the most interesting parts about this, I think. So in some way, somewhere along the line, that person has been, I guess, building a set of preferences that makes them probably more comfortable to, choose smoking or something. Because there's some reason that this person has to be choosing these things, because maybe it makes them feel a certain way about themselves or about how they fit in the world or something. Um, it's probably so.
Okay. I think I understand what the general theme is about active inference explanations. And is that if there seems to be discrepancies between those two level preferences, the system base and experimental base, then the explanation should be sought in the complexity of the model, which seemingly can, for example, can contradict the lower simplistic systems of the model. So that the answer is always then to be sought in the complexity of the system. Is that, you think, the right, like, how else?
I think Malcolm's trying to talk, but I can't really hear him.
Go ahead, Malcolm.
I think it's
Okay.
just a volume thing,
Yeah,
Malcolm.
I mean, short answer, yes. Nested models or interacting models often, this is true of a linear regression model. This is just general to any kind of explanation of variance. If something is not being explained by a model structure within a level, often it's accounted for elsewhere. But like before jumping to the psychological connections of the terms like preference and trying to associate it. Like you gave an example of a behavior. So even just speaking really broadly with a single layer behavior. So it could be that the habit, the E, the prior on action is such that a given action is selected, like turning a certain direction. Or you could localize the repetitive behavior's causality in the B. So the person they don't understand the consequences of a given action. Like their skin itches and they don't know that not that doing this will do that. Or it could be in C, in preference. It's like, so the structure of the inquiry is to develop these kinds of precision psychiatry or cognitive models to differentiate hypotheses. So thinking about it qualitatively, speculatively, mixing ontologies, combining experiential and technical elements, those are early and sort of generative phases. And then, yes, you start to specify generative models following like the chapter 6 type recipe or using other approaches. And then you start to look at the relative merits of these different approaches. Let, let's return to, yeah, okay, Martin, go for it. But you're muted, but then continue.
I
Yeah, I don't want to stray the topic too much on one end, and if someone else wants to speak as well,
Yeah, let's please return to chapter 2.
all right,
And if
thanks.
somebody has a
I
specific quote or question or idea about chapter 2.
I just wanted to add one more idea I had of your question, Martin, like the idea of contradicting preferences and how system would, like, as you said, maybe you want to smoke, like you have this preference of wanting to smoke and not wanting to smoke, and how this affects your selection of a policy or an action. And actually, I was just reading yesterday a nice paper of like the attachment style of where this experiment where the children are playing and then the mother gets out and they are crying, then she gets back in, and depending on the attachment style, the securely attached child will be angry but still get to the mom and knows what to do, while the disorganized child will like be in a unsettled mood when the mother gets in, and it's not really like a clear policy. So there's a high uncertainty, like when you refer to the active inference selection, policy selection calculation, a high uncertainty what policy is actually the best policy I should choose in that moment, given the observations I have and the contradicting preferences. Uh, um, so
Something.
Wait, Ben's lagging a little bit.
say like
Yeah, okay, so it's not me.
the example you offered with the smoking will maybe behavior as we maybe see quit smoking, but I don't know.
Thank you, Ben.
Yeah, just a short comment. Yeah, I do acknowledge like there's a lot of explanatory power in active inference. Yes.
Okay, awesome. So let's kind of return to chapter 2. Anyone, write in the chat or yeah,
So I can start with something in chapter 2.
sure.
So one of the sort of questions I was trying to follow along in the chapter to see if there was an answer for is essentially like how a decision is actually made. So they talk a lot about a couple times about how there's like a balance between these two terms in the variation of free energy, right? How one of them is like, is about exploring the space and one of them is about exploiting the space. But I wasn't really clear on how a decision is actually made. So they talk about how like um, the policy is like the relative balance between these two terms, but at what point is a decision made? Is it like, is there a threshold somewhere that like an agent actually uses to say, okay, actually I need more information, so I'm going to explore the space more versus like, okay, I want to obtain this preferred state more than I care about getting information, so I'm going to um, you know uh, seek out this state or something. It like, I guess my question is there a threshold? Like, how is a decision actually made?
Yeah. Sylvia, do you want to add something to that?
Yes, and I feel like maybe that threshold could be determined by that agent's priors or preferences to begin with. For example, even personality, some people tend to be more risk conservative while others are risk takers. And in a way, that threshold would differ from those people. Or we look at people with psychiatric disorders, they have very rigid priors about the reality that it's clearly kind of maladaptive even. But to them, it makes sense to choose certain policies or make decisions at a certain point, while normal people might think that, well, that's not rational or that doesn't even make sense.
Mhm.
So I guess the threshold might be very dependent on the context and also the agents like priors to begin with for that specific like goal or desirable outcome that they are pursuing after.
Okay, so there is a threshold then, that is the idea.
Yes, I believe so.
Another aspect of this, just operationally,
Yeah.
when you implement these models, is here's, one tutorial, one place to look at this is you have a prior on policy. So that's before the observation comes in, how likely are you to do different things? 50% to turn left, 50% to turn right. An observation comes in. The policy prior is updated to the policy posterior through the calculation of expected free energy. So the prior on policy was even, and then the pragmatic value and the epistemic value of these two alternatives reweight them. So now it's 70% likely to turn right, 30% to turn left. And then from that posterior distribution, one action is sampled. And then that is emitted. So
Okay.
in this simulation, every time step in action is decided. Now the question of when an action is taken is done with a few different approaches. One approach is to have a null action, like have weight as an action. Another approach is to have a nested model where at the highest level of the model, you have weight or act. And then within act, you have just the choices of action.
Gotcha. Okay.
So an action is selected because there's an unrolling continuous action. So then it's just, are you trying to model something that happens at every single time step, like gas or brake? But then if you want to include neither, you could either include that in the base level, or you have this nested model with, and then that's where you'd get into variation in those cognitive parameters. What are someone's priors on how likely they are to use the gas or the brake? What are the B matrix reflecting people's understanding of what happens when you hit the gas or the brake? What are their preferences about what they expect to see and prefer to see from sensory observations achieved by hitting the gas and the brake?
Got it. That makes sense. So it's like, yeah, it's a sampling of policies, not just a simple threshold. It's a sampling of actions over policies.
One action gets sampled. So
Mhm.
carried through time is a distribution over action choices, and then that gets sampled one. I mean, this is a great line. And this is like when it's like, wait, what is active inference? This is an important thing to walk away from chapter 2 with. What is the simple but fundamental advance offered by active inference? And this is the question.
Mhm.
So that's an interesting thing to ask and learn. And how does that fit into the low road? Okay, let's look at some of the questions in chat quickly. Okay, John, would you say preferences are revealed by priors, which are revealed by observations? I mean, revealed to whom? When you're the one writing the generative model, you wrote all those variables in your code. In a given situation where you're reducing your uncertainty about those parameters, you could imagine a situation where you're reducing uncertainty about one of those variables based upon your assessment of another one. But sure, there could be a situation where through observation, which is kind of the ultimate empirical interface, you are learning about priors, but priors are a bit broad because priors in Bayesian statistics refer to basically anything before they get updated. But then they become the posterior relative to them being prior to that observation, but the posterior is again prior to the next observation. So it's usually a little bit more helpful to specify like prior on what.
Can I answer that
Yeah.
also to John? So, yeah, I was thinking about this just a couple of days ago. This is really interesting because what do you have when somebody, like, say somebody experiences something new for the first time? Maybe I don't know, they've never gone like rock climbing or something, and they've never seen it before, and then they go, and all of a sudden it's really exciting, and they have all these different experiences about rock climbing or something, and now they love it, and they didn't know that before. So in that case, their priors were revealed by observations, right? Like there has to be some mechanism in this where somebody can like be adding onto their priors because there has to be new room for new experiences to be had. So in to that question, I think I would say yes.
Yes. Also, great point. Also, within the textbook, like within the early part of working within a single layer model and so on, it's a structurally fixed model. So the thermometer is dealing in degrees temperature and it can quantitatively adjust within degrees temperature, but it's not going to start seeing or modifying color. That gets into the space of structured learning, where you have model structure as an inference target. And that's where the assembly of new concepts and changes in the structure of affordances or anything come into play. Okay, Andreas, what's the difference between predictions and preferences? So, as used here, preferences are a prior distribution on observation that reflect expectations over observations consistent with being a cost or a constraint function, also sometimes called preferences, and it's used in pragmatic value calculation. Predictions are anticipations about something, usually about observations. Okay. Anyone again can write something or raise their hand, but
Chris, you could write that down somewhere.
it's all recorded. You can return to
Okay,
it.
yeah,
But
keep
yeah,
going.
and also these definitions are the active inference ontology. So
Brilliant.
the definitions of terms and just it's just about understanding where is it referring to, like continent scale, like prior again, but it could be a prior on anything. So there's little that can be, you can't go too much into saying what about this prior because it's just like a prior on what. So a lot of it is just knowing when do you need to just add more detail. And when it comes down to it, it's about the specific generative model constructed. Um, but thinking about the structure of the book a little bit. Remember, we're in the first half. So we're in the background and theory and learning area. Chapter one was introductory. Chapter two and three are going to bring us to active inference from two different directions, the low road and the high road. Chapter two is going to do this from the low road. Chapter three is going to do this from the high road. Chapter four is going to be the active inference generative model, which is kind of like this boundary artifact, which is the target of our construction. It's used in computational inference. Looked at from the low road, it's constructed according to some of these topics. Looked at from the high road, it's consistent under the free energy principle. Chapter four. Chapter five is a review on a few different generative models that have been constructed in mammalian human neuroscience. So that's the first half of the book, is introduction and then two roads converging on a certain type of artifact that we construct. Chapter five, giving examples of how that artifact is used. So it's going to be like two different complementary approaches. The low road is like a build it from the ground up, computer science or engineering, starting with probabilistic modeling and Bayes equation, working towards building integrated models that have both perceptual inference and planning or action selection as inference. That's like the build it from the ground up. It's like if you were building a cognitive framework for an agent, embodied or cyber physical or whatever it was, and you wanted to combine the inbound signal processing elements with the outbound action selection control theoretic elements. And you wanted to integrate the inbound and the outbound into a unified model and then apply it to things like brains using tractable approximations like variational inference. That's kind of what happens on the low road, is like building cognitive models that unify perception, cognitive phenomena, and action in a ground up way. We'll get to chapter three in the high road when we get there, but that's sort of the low road. And that's how from just primary considerations in statistical modeling of cognitive systems, one reaches something basically like active inference just from considering the question of modeling agents. That's in figure 1.2. But then chapter 2 goes into this in more depth and starts with this, again, kind of step by step, bottom up. But for those who haven't seen much of Bayesian statistics before, this is kind of a good motif. Like We have a prior belief about objects in our hand, whether they're frog or apple. Not a secret third thing. Again, that would be the structure learning. And then an observation comes in, and the beliefs about the object are updated. That's perceptual inference. And something analogous occurs with action inference, where we have a prior on what we are apt to do. Then the observation comes in, and then we have a posterior on what we're apt to do, which gets sampled from. And that was kind of the question earlier. Okay, anyone want to ask something, or I can copy one of the questions from the chat? Yeah, okay, Henry.
Yeah, hi. So I have a question about equation 2.5. So the
Yes.
variational free energy definition.
Yes.
So I guess these are two quite simple but interrelated questions. The first is like in the complexity versus accuracy factorization. Sorry, the divergence in evidence factorization. The divergence is like computed with respect to the approximate posterior, when like canonically you'd compute this with respect to the true distribution. Is this just because if it was the other way around, it wouldn't be equivalent to like the energy entropy formation, and it's a like a post hoc justification, or is it more like purposive than that?
Um,
Does that make sense?
can we talk freely, or sorry, is it like directed questioning, or can I just?
Well, respond to this question if you have a thought.
Yeah. Yeah. So my understanding there was that it was with respect to the variational because we don't know the true posterior, right? So that's, I mean, that's the whole point, right? Like we use Q because we don't know what P is, so we approximate it with Q.
Yeah, I was just wondering because like that final term, like the additional quantity over the true evidence, like we can't compute that anyway because we can't compute the true posterior. So we'd use one of the other two factorizations to like plug in the numbers, and we show they're equivalent to the third. Is that correct?
Yeah, two answers here, just practically. One of them is when you implement the equation, these three decompositions are equivalent, but when you look at the code, like for PyMDP or something like that, you will find it's often only implemented using one of them. And there's probably situations where implementing using one of these decompositions or another have different computational performance. A second answer that's really important is you pointed out that the evidence term is fixed and doesn't depend on Q. So when we're interested in variational gradient descent, the evidence term is actually a way to kind of quarantine the overall likelihood of the data and only follow delta F, which is ultimately what we're going to use anyway. That's why the overall actual F will be like 8314. But that's like looking at the least squares error for a linear regression model. It doesn't matter what the real number is. It's about within a model, like following the gradient on it. So this is a really good way just to say, well, whatever the evidence is, whatever the likelihood is of the data, we're going to minimize the divergence. By doing so and following that tailwind, minimize the variational free energy, whether that convex optimization happens to be up here or down here. Sylvia?
Yeah, I have a more general question, but just adding to Liz, I was thinking when we talk about free energy or variational free energy and saying that it has an upper bound, is it correct to actually perceive it or simplify it as like, to see that it could be an overestimate of the actual surprise, the surprise that we can't really, know the true uncertainty that is out there, but we are giving it an estimate to make sure that we can reduce it regardless, by our model. Like, is that a correct way of perceiving it?
Yeah, absolutely. So when the process generating observations is the same model family as the variational distribution. So Gaussian process in the world, and we're going to use a Gaussian variational estimator. Then the variational free energy will converge to the actual generative function. Whereas if the generative function in the world were something just weird or were bimodal, you still, within the variational family of choice, would be doing the best you can by reducing the divergence. But that could be hopelessly far away. So that's why it's an upper bound that's always equal to or greater than. Because the best you could do would be if the variational family were the right family to exactly become congruous with the data generating function. But in the situation where the data generating function is anything else, then you'll be minimizing your variational free energy to some point that is slightly not exactly minimizing surprise on the target distribution, but it's the best that could be done within that constrained, easily optimizable, interpretable family.
Yes, that makes sense. The general question that I had was, as we were talking about advancement, what are the key implications of active inference treating perception and action as part of the same cycle with this shared objective rather than the separate processes with like distinct goals? And how does this unified framework, this coherence, apply to real world? I'm just really curious about how everyone sees the potential of active inference in relation to like advancing their fields. Because like for me, with someone having a background in psychology, I think it's a really nice way of putting very fragmented theories in different branches together and to have like one unified explanation. So I'm just curious about, how other people are taking it from the perspective of their fields.
Anyone can go for it, but those are awesome questions. That's like literally the whole fields. But are we going to have a special theory for every brain region, every cognitive phenomena, or what happens when we do have unified approaches? Yeah, Monton, then anyone else.
Yes, I was just also like wondering because I do not know the scope of active inference explanatory power, so I also know its limits. So I was actually interested, are there any like limits that what we can speak of about till we can only use active inference for these matters, but not for these matters? Is there anything, or do you guys, if you, Daniel Friedman, I think you're most well read on active inference, think it's everything that they can explain?
Anything could be modeled, but whether to any one, any given model of a given thing is satisfactory is a totally outside question. So the explanatory scope of the framework generically is similar to like saying, well, what's the explanatory scope of statistics? You could model any distribution, but does it say anything about the height of these children in this classroom or why this happens here? No. But could it be used to model why that happens there for that thing? Yes. Is that a tiny engineering project or is that a mega engineering project? That's the question. Is it something where we're going to reach a satisfying account easily?
The purpose, I kind of, I forget who's the name of the psychologist, the lady psychologist. Anyway, my own purpose is trying to figure out how to integrate or find coherence across dimensions that are operating when you watch a movie or a video. Basically, the text or the copy, the cinematography, and the music They're all coming in through different perceptual systems, but they have to create a unified immersive experience. And the predictions we're trying to make are audience responses. I've actually done some experiments with that because we have ways of separating the cinematography from the storytelling, from the meaning being communicated by the music and how that parallels the meaning being communicated by in terms of semantics and so on. So that that's that just as a way of saying how I think this stuff will apply. I'm trying to predict audience responses to creative, and it turns out AI is really good at coding the creative and making guesses already about what's going on. And then when I show it actual audience responses, like, oh, well, I was wrong here, I was wrong there, and so I'm trying to improve the model over time, and that's actually why I'm in the class.
Awesome. That's going to come up like in chapter 6. There's some latent underlying phenomena like a frog or a well-performed multimodal performance.
Well,
And
actually, an interesting thing we just ran across the other day. I don't know if you ever heard of T.S. Eliot's objective correlative.
no.
It's a literary theory that the Nobel Prize winning poet T.S. Eliot came up with, basically saying that if you want to evoke a specific emotion, there is a unique sequence of objects in your perceptual world that if you go through that sequence will evoke that very particular emotion. So that there's actually an objective sequence of perceptions that lines up with your associative memory system. Basically, I wrote an essay with it and stuff. I'll try to forward it to the group.
Cool. I mean, this is kind of a general Mad Lib structure is reapproaching X from an active inference perspective. Like,
Mhm,
what
mhm.
was pragmatism about? Or what was this about? Or
Yeah,
how could this be? And yeah, those are,
yeah.
especially if those connections haven't been made, writing those pieces out and footnoting it is an awesome way to open up your thinking and footnote it and also
Well, if you
take
take it one step further, it's actually a way of generating new data.
that too.
So the goal is obviously get to a self-learning situation every time you connect ideas, because you're making connections that the AI isn't. It's a continuum. It knows a lot of stuff, but if you connect the dots for them, you're like being a neuron in the thing. Basically, it can create new data on meaningful connections that it wouldn't see without your help. I think that driving towards a central role for human beings in the interaction with AI and the theoretical framework being something like active inference. So.
Okay, Monten, then Adam.
I was also very interested in thinking about how to interpret what active inference is doing if you're like a modeler in mind. So there's like some higher goal to be happy, for example, and to be happy, you have to find a sub goal, like a method for that, and that in itself also becomes a goal. And then you ask for the same goal, how to achieve this, etc., etc. Then you kind of see this scheming down way. And how does this thinking relate to active inference and how they choose certain policies, like a sequence of actions which generates observations in line with some prior? Is this notion of higher will, low will to be seen in the nested models, or should we like relieve all these notions of old and only think of active inference terms?
A lot of ways to go with that. Like, keep that feeling and channel as open as it can be, and really look at the textbook for what it says. And then whether those Lego pieces were exactly what you sought, or whether you see that you need to build up a ton of pieces to get to the sophistication and the interplays that you're talking about, then you'll have the grammar to go about that. But you may find that it's literally addressed within a single layer and that you're talking about the interplay of two kinds of variables within a simple model at a single layer. Or you may find that you're thinking more about nested models, and then you'll have the grammar to actually go about building those. Adam?
Yeah, I was so regarding equations 2.5 and I think 2.6, etc. I was wondering if those are derived anywhere mathematically, and because it seems like they're derived sort of heuristically. Is there anywhere where I can see where they're actually
Yeah, yeah.
or
So,
not?
um, here in the equation rows, um, here, and these are just tiny examples of the absolutely transformative contributions that people can make. First off, with their written questions, also with derivations if they understand. So this is, I believe, from Jakob Smeckel. Here is equation 2.5.
Oh,
These are materials that aren't in the textbook. The textbook is just like the tip of the iceberg, and
yeah.
we can go a lot further and connect a lot of the paths. So here's 2.5. One of the big pieces about 2.5 that like really helps clarify it is the route of derivation is actually row one goes to two and row one goes to three. There
Yeah.
may also be a path to go from two to three, but that was very helpful to understand that there's a path from one to two and one to three. Um,
I mean,
and
there should be if they're equivalent, right?
yeah,
There better be. Yeah.
yeah, I'm sure there's a way to do it, but
Yeah.
just in terms of ones that can fit on a single
Sure.
slides.
Yeah.
And then 2.6, um, Jonathan Schock has, let's see if this link still works. There may be another updated or published version, but Jonathan Schock, who's a math professor, um, yeah, he's done some derivations on expected free energy as well.
Okay, nice.
Yeah, so those are good. Yeah, here's his, and this is in the math learning group. So like, it's
Okay.
also that people have all these questions. Like, that's literally what the questions are for. Is
Yeah,
just
cool.
add a question and write it out. Everything that people are typing in here, adding the resources that are relevant. Like, please, in the time between, enrich what we have and add more and add your thoughts. Like, imagine that these questions are being asked by people right now, and the ones that you're excited about adding information to, just go for it.
Okay, nice. Yeah, there's a ton of material on this
Yeah,
website. I haven't really gotten to half of it yet, so
yeah. Oh, this is also kind of a fun piece about applying active inference to topics. Like, this was just done with all by all. I generated synthetic domains, and then I just applied each domain to and from active inference using LLM. So this got ridiculously far
wow.
in starting to apply active inference to, ATM transactions and blockchain and chemistry and things like that. So
Okay.
understanding how to even use the extents tools to project to and from active inference ontology and techniques is already extremely productive.
Okay, very cool. Thanks for
Awesome.
that.
Yeah.
Was someone else gonna say something? 'Cause I have one more quick
Yeah, go for it.
so on page 37, figure 2.6, I kind of wanted to understand that diagram just a little bit. I think I do. So, my understanding of this is saying, okay, so like at the top level, there's the equation for the expected free energy, and then below it are different decompositions you can make if you omit certain terms. So, like, would that or does that correspond to like if you know you have a different, I don't know, like the decision-making regime in your certain use case, would you decide to omit a certain term because you're trying to um, I don't know, like structure the learning that way or something? Or like, how do you know when you want to admit a certain term or et cetera?
Yeah, great way to put it. So this is like equation 2.6, where we have the expected free energy here. Usually, people talk about this first decomposition between the epistemic value, expected information gain, and the pragmatic value, the preference or the constraint satisfies. But again, these are equivalent or bounded derivations. Now, in this figure, here's pragmatic value, here is epistemic value. So just briefly, and these equations also, again, another area where people can look is using the ontology. Here's natural language ways to read these equations because the letters don't matter. It's about the ontological relationships.
Sure.
So this is free energy, expected free energy on pi, the policy prior distribution, is an expectation about the variational distribution, about the expected sequence of observations, y tilde, conditioned upon which action we're going to choose, about how likely those observations are in light of our preferences. That's pragmatic value. How likely is the observations, how are those observations going to be linked with our prior preferences on observations? And then epistemic value component, the double line is like the KL divergence separator.
Yeah.
Looking at these two sides, they're pretty similar. Like they both have Q x tilde conditioned on pi. So that's my variational distribution of what latent states I expect to unfold conditioned upon the action that I choose. The difference is here we have what is my variational distribution on the observations that I expect to see conditioned upon the latent states. Here is the observations I expect to see also conditioned upon the action. Those are what those mean. So this is saying if the action is not expected to change anything about the observations received, then the epistemic value of the action is going to be low. Whereas if conditioning upon the action leads to a large difference, then it's going to be high. Okay. Now you brought it up in the context of like wanting a certain regime of action, specializing to get by dropping out one of these terms, you get certain subtypes. That's kind of the break the puzzle down. The build the puzzle up is you will find many thousands of articles discussing these topics. Here's a way that we can see that those are special cases of a more generic optimization target function. So if we only have pragmatic value, we get expected utility theory, Bayesian decision theory. But what would be the issue with that? Well, we wouldn't be able to have learning. What is the reinforcement learning approach to that? They try to bring learning into the reward function. What if you drop pragmatic value? Then all observations are equally preferable. So behavior is driven by just surprise and learning. And that's like novelty search or pure intrinsic motivation. So this is sort of revealing and clarifying that expected free energy is an integrated decision-making imperative that contains some blend of a pragmatic value and some blend of an epistemic value. So whether we choose now to zero out some of those sections to get certain behavior, or we just want a new lens to look back on the last decades of signal processing and control theory, this is just a helpful way to see that.
Okay, that makes
How
sense.
to interpret 1, 3, 4, 5?
Yeah. KL divergence between what observations I expect to see conditioned upon the policy and the true distribution of the observations conditioned on my preferences. So this is like KL optimal control. And this, you know, is used as an objective function in some control theoretic settings.
Mhm.
It's
Because yeah.
Yeah, and there's other imperative functions that can be drawn. For example, like Baron Millage and others have clarified, like, well, there's expected free energy, and then there's free energy of the expected future. So, you know, there's some other imperatives that you could draw up. It's not like this is the only way to do policy updating in active inference.
What do you mean with that exactly? In the sense that the variation of free energy is the way to go, but in expected free energy, there's discussion about what the right way is.
I'll like link this in the chat. This is from 2020. Here's another future-oriented imperative function that still is a free energy, so it still can be used for variational gradient descent. And this is just another family of imperatives to use for policy updating.
And this is only the case with expected free energy. In the other variation free energy, there is the consensus of this is the thing to do.
Yes. There are different ways to approximate variational free energy. Like this is with Noor Sajid, and it's like, okay, it's a slightly different approximator. So there are some flavors and choices. It's not that there's some finished singular answer, especially when you start getting into the level of data sets. There are some implementations that may work, for discrete or continuous or different other features of the specific issue. But again, this is like why low road and high road is so important because the high road and the analytical directions there, they're system agnostic. They're data set independent. They're not talking about computer languages. It's not the operational order about what comes before this and how does this variable relate to that per se. On the low road, that is the whole discussion. And then the generative model is the artifact that is entirely constructed to be viable under those analytical top-down descriptions.
What is the total discussion in the low road that contrasts with the high road? The kind of specific implementation? Or?
I mean, contrast or complement. Again, that's what chapters 2 and 3 are about. And then we meet back up in chapter 4 with a train station that can be reached from both roads. Because in the low road, we're talking about building these unified Bayesian cognitive models that deal with the inbound perceptual and the outbound action selection, period. That has much to do with cybernetics, end-to-end variational autoencoders, and so on. Top down, we're not thinking about one specific computer implementation, let alone like a data set or a computer language. We're thinking about the analytical descriptions of things in their persistence and change. And then the active inference generative model is something like a variational autoencoder, asterisk, something like that, but it could be that is compliant and describable through that high road channel. But the models that we're going to look at in chapter 7 and 8 in discrete and continuous time, those are the kinds of generative models described in chapter 4, which are reached at from chapters 2 and 3.
Just so for me to understand, also the high road delivers one true value of the variation for energy. That is, it delivers one, but it is like open, and then there are different ways to approximate it. But the high road does leave out space for what the exact expected free energy formulation should be.
I'm sure people have different responses to that. I would say there isn't a singular true variational free energy for a system because that's a feature of a model. So the variational free energy is like an observer approximating a variable. So if we were talking about, well, does the temperature in the room have a real L2 norm, a real sum of squares? No. Different observers could make different linear models and they would yield different sums of squares, different R squareds, different p-values, etc. Is there a true ANOVA F statistic for the effect of this on that? Or are there just statisticians who are making different ANOVA and reporting their results? So that's the instrumentalist angle, which is people can calculate the VFE for a model, but the map is not the territory. So there might be a VFE for a map, but a map isn't the territory. So that VFE doesn't describe the territory because somebody else could have chosen a different variational family and then they would have gotten a different VFE.
Basically, everybody has their own queue, right?
Yeah,
Everybody is their own queue. That's what queue is. I mean, queue is like the individual making, a model of the world. That's where the queue comes from. That's the approximation. It's me as an agent trying to understand, and I have this generative model that I make of the process, right? Is that the idea?
exactly. And so everywhere you see a queue or everywhere it's talking about a map, this is like a sort of that's why Toby St. Clair Smythe in his dissertation in Livestream 54 on the category theory accounting for the active inference generative models, he calls it the compositional cognitive cartography. So this is like the science of the map making because it sets up the accounting structure for making maps. But then how coarse grained should the map be? What's the scope? What's the angle? What's the ortho project? I mean, there's so many questions. Even if we were just making a map of neuroimaging, which again returns to SPM, the statistical parametric mapping, making maps of activation in brain regions or of inferred neural activation patterns from neuroimaging, and then going from that map of activation to the posterior probability maps. So statistical transformations of those maps. But by the time you get to realizing that you're dealing with the probability transforms of neuroimaging data, including all the steps of like registration and processing, any statistic you get out the other side, it's pretty easy to see that that's a feature of the modeling process, though it has a causal relationship with the brain. But it's not like there's just one p-value, nor is there one posterior, nor is there one VFE for a given experiment. And that experiment was just one of many that could have been done. Okay, not sure I'm going to copy some of these great comments in here. Let's go to the like again, there's like so many fun things hidden in here, and what isn't there is for us to add and enjoy. Okay,
Nice. I have to run. It's
thank you.
past time. This was great. I hope to join the next ones. Thanks for all the links in the coda. I'll check those out.
Yep, thank you. Okay,
Bye, everyone.
okay.
Yes, thank you.
Okay, so Nacho wrote, I always wonder if there is an estimation of the actual number of levels layers present in different species. I believe the number of layers determine the inference abilities of the animal. Is that right? Yeah. In fact, this is an interesting thing that Carl Friston will often say, oh, well, like we make models with 6 layers because there's 6 layers in the cortex. But I've always been a bit perplexed by that answer because each cortical layer, though it has 6 histologically distinct strata, is actually one unit of nesting from a cognitive Bayesian perspective. So, how would you determine the number of layers? Well, there might be a situation where you can tease that out experimentally. But how does it relate to structure learning? You could have inference on how many layers should I make this model. And that's kind of where things are at in terms of like neurosymbolic programming and procedural generation of active inference generative models is exploring model classes that include different layers and types of nesting. Then Ben added great points. And there's several papers that have this sort of two-stroke engine, which also corresponds a little bit to expectation maximization, EM optimization on structure. Okay, any last comments?
You're muted, Charles.
I said Ray Kurzweil has a nice book called Creating Minds, which speaks to the 6 layers in the cortex as well, I think. So he's in agreement with Carl.
Yeah, the 6 layers are simply anatomical, even though there's like sublayers and blah blah blah. But the each cortical stack is actually, here's the 6 layers right here. Each cortical column is one layer of a Bayesian hierarchical model. So even if there was only 2 anatomical layers or 35 anatomical layers per column, you could have a linear concatenation of 75 columns. So people focus on the 6 because it's clear that there's something repetitive and important happening with the cortical layers. That can be seen histologically from like an evolutionary perspective and all these other things. But there's no limit to their concatenation laterally and how many nested layers that could have. But if you look at this from like a generalized coordinates perspective, like you have the position, then the velocity, then the acceleration, you keep on going up the derivatives, you could look at real time series and find out how much variance is in these higher moments. And after you get through a few moments, there's not much to explain for most time series.
Would you say that another way?
Yeah. If you want to explain or track the movement of a particle, like a car in traffic or Bitcoin price or your blood sugar, just there's some particle that's following some sort of like really
Yeah, I got it.
The first moment of the statistical distribution is its position.
Right.
Then there's its velocity, like just the vector of its direction. Then the acceleration, how is that velocity changing? These are like derivatives. So that's called generalized coordinates. For real time series, you can ask what fraction of the variance is being explained as I add more generalized coordinates. And this is an empirical question, so you could construct one that has a lot of explanatory value at the 12th derivative, but just empirically, the explanatory value starts to get eaten up really fast. and higher derivatives are overwhelmed by noise and they're slow. So over shorter timescales, the lower derivatives, which is to say nested models that would have a few layers, explain lots of the variance.
Yeah, I got
How many layers and how much of the variance you need to explain over what time scale is 100% empirical.
when you're looking at the cortex horizontally rather than the 6 layers vertically, how does recursion operate there? I'm not a biologist, but I'm just curious about how recursion operates.
That's a good question. Yeah, there's a lot of ways you could get reentry as recursion,
Uh-huh.
or reflection and reflexivity as recursion. Nacho?
Yeah, when I was asking the question, I was also thinking not just from a neurological perspective, but also from the perspective of psychology of perception. For example, if you're perceiving something and you say in any of the examples you said before, as in a person that is deciding to smoke and everything's mixed up in different layers, different levels. First, you have to know that what you have in front of you is a cigarette. So that means that you have built from the input, the sensory input, you've built like a concept of what it is a cigarette, which is made of different lines and points, and that goes from the retina the thalamus and then to the cortical layers, then goes to the cortex. So what I was asking is if there is an estimate of the number of layers you need, because in each layer you make a different abstraction. You start by raw data, raw points and lines, and then those lines are connected, and then you can see how a table or a bottle or a cigarette is made from these lines. And I guess this is like a new layer from raw data to a concept, and then as you go further up in this ladder, you get more abstract concepts. You know what I mean? I'm not sure if I'm
Oh,
explaining.
yes. Like this is well studied with Friston and others, and this is flowing through brain regions with the visual cortices.
Mhm.
So there's like but there's yeah, the visual processing chain just to get from photons hitting the retina to just the acknowledgement of this is a given object. A lot goes on there.
Yeah.
But in cognitive modeling with a matrix, you might just say, all right, we have a noiseless or a noisy matrix that just identifies it. And that's kind of
Mhm.
coarse graining over all of those like edge detection and shape detection steps. But if you were studying the neuroscience of vision, you might delve more into looking at these visual cortices and the what and the where stream and
Mhm.
all these
Yeah,
other
yeah.
things. Yeah.
I teach this at university. I'm a professor of this. What I am trying to do is to connect what we know from this perspective, these classical studies of visual perception, to the inference model, to the number of layers you need in the model to explain this kind of stuff.
Yeah. Awesome. I look forward to continuing to unpack that. And chapter 5
Okay, okay.
is probably going to be a great one for you because it's going to focus on these three human neural systems.
Mhm.
And that'll kind of give a little bit of a playbook with many, many references to papers,
Mhm.
but doesn't look at the visual. But there's a lot of other good visual papers.
Okay,
Cool. Okay.
thank you.
Can I ask you one last question?
Okay, go for it.
This is top of mind. I'm going to bring it back to movies. That's my focus is figuring out how movies work. And there's a phenomenon in the movies, because surprise is a big part of making a movie engaging. But even if you're watching a bad movie, there's a thing called closure where you're watching a bad movie and yet you'll sit around to the end just to see how it turns out, because it's like the brain is building a model of the world that's going on in the movie, the cinematic universe that you're experiencing, and it kind of wants to know the final answer before it leaves, unless it's super boring and so on. Is there something in the model that would address that psychological phenomenon of the need for closure?
I'm going to give a similar answer, which is really learn the textbook, learn the grammar, and then you will construct many different hypotheses about how that could be. Like there could be a person who prefers, I'm the kind of person who finishes movies, or my culture expects me to finish movies.
Right.
So then, independent of whether that's their favorite color on the screen or the narrative is unfolding according to their preferences, they still would fulfill this other preference. But then that would be where you design these different kinds of differentiating hypotheses with optimal experimental design to get at that. But there's a variety of ways that independent of someone's visual hypotheses, they could have narrative preference. Independent of narrative or genre, there could be just behavioral expectations. There's so many reasons because now we're talking about not just even the narrative processing, we're talking about someone's interplay between their own bodily logistics and what they want to do with their own attention in their day and their uncertainties. It's just like, yeah, I don't care if John and Sally end up together at the end of this movie, but I'm gonna watch it anyway. But that's like
Well, I'm just wondering if is it a preference thing or is it a need for is it a testing the model in terms of I built a model of how this movie's working. I just want to see if the model works.
you don't close off one road with it. Is it A or B? Just say if it were A, then the generative model could look like this. If it were B, the generative model could look like this. Now you'll have two.
Okay.
How would I differentiate between if it were A and if it were B? What else could there? You just keep on unfolding, and that's what the structured inquiry starts to look like, not going from a qualitative and just saying, well, is it this or that? Well, that doesn't sound viable, then just go with this one. But you sketch them out, and then you kind of build up your space of models that you're considering, even loosely, but you can do this computationally depending on what you have available.
Mm-hmm.
And then, well, if it were A, what would we expect to see in this data set versus B? But if A and B give you the same result on the data set, you're not going to be able to distinguish them. So what data set would you need?
Mm-hmm. That's a good answer.
But
Thank you.
yeah, it's not just about a vibe check up front.
Okay. Thank you.
Okay. Thank you all. Till next time.